and welcome back to part 2 about inferential data analysis. Remember that I want you to think about these things conceptually. I do not expect you to know how to do every analysis. That will be way beyond the scope of this class. In the last section, I talked about how when you're doing inferential analyses, you're ending up with a confidence about your inferences about the population based on the sample. And basically you're asking yourself, did the change in the sample happen because of an intervention or by chance? So when we do this, you will find as you read these research articles that the concept of hypothesis testing is woven throughout them, and you need to understand this if you're going to conceptually understand inferential statistical analyses. What we do is we start with the hypothesis about the intervention or the prediction. This is a statement, and it should be connected to the general problem or the question that's the reason for the research. So I make a prediction about the intervention, basically. I say that if students get an hour's exercise a day, their math scores are going to go up. Or if if I use manipulatives 5 times a week in the classroom, second graders, that their attitudes towards math will improve. Anything like that where I'm making a prediction before I do the work. And I make that prediction based on the theories and the research that I do and the literature review. The research question could be something like, does annotating samples of informational text improve 7th graders' writing? In other words, I'm wondering if I can teach 7th graders this strategy about annotating informational text so that they can notice and pull out the different components of informational text. And will that in turn have something to do with improving their own writing skills when they're able to do that? Kind of like using a good model of writing, will it help them? But then my hypothesis doesn't ask a question, it's a statement. I'm going to say that 7th graders who annotate, etc., with all the details in there, will score higher on the writing test than a control group. So I'm making a prediction about this intervention that I'm going to use and how that will affect the students in the intervention. We use the concept of a null hypothesis as part of hypothesis testing, and you will see this term often in research articles if they involve inferential statistics. A null hypothesis is a mathematical statement that you can show to be false. Let me repeat that because it's so important. It's a mathematical statement that you're trying to show is false. So we denote it with an H and then a subscript with a 0. That's your null hypothesis. And here's how in that third bullet down, I've got an example of how it's read. What I'm saying, my null hypothesis, and then I put a colon, is such that the mean of the intervention group, when a line over X means the mean of the intervention group is equal to the mean of the control group. Now, obviously, when I do my study with this intervention, whatever it is, I want to show that that statement is false. I want to show or show with confidence that the intervention group does not equal the control group's mean. The null hypothesis is sometimes called the hypothesis of no difference, because what it's saying is there's no difference between the groups. There's no difference between the intervention group and the control group. Obviously, that's why I'm doing the analyses. I want to show that that's false. Or sometimes it's the null hypothesis is saying that there's no relationship among the variables if you're doing regression types of analyses. In red, this is very, very important as you read inferential analyses. You always assume that the null is true. We are then trying to find evidence that the null is false beyond chance or our sampling error. We're trying to show that the null is not true and how much the probability is that that could be just by chance, whatever we find. Now, people always ask why. This whole concept of a null hypothesis is just really, really aggravating to people who don't work with statistics a lot. Well, there are some important reasons. And basically, if you don't have evidence to the contrary, it stands. The intervention group is equal to the control group unless you can show me some evidence to the contrary. So the status quo stays without some evidence. So obviously, when we work with inferential statistics, we're trying to reject the null, and we're trying to come up with a really high probability or confidence that the difference in the means is first of all large enough to detect, and that the probability is really small that the results are by chance. And you will see statements like the probability is less than 5% that the results are by chance. And that lets us conditionally accept the alternative hypothesis. We don't ever prove that an alternative hypothesis is true. So an alternative hypothesis is your research hypothesis. And it's basically that there's a difference between the samples that's not just from chance or from sampling error. So you have a null hypothesis, status quo, no evidence, and you have your alternative hypothesis. You are not trying to prove that your alternative hypothesis is true, ever. What you're trying to do is find evidence that the null hypothesis is false. And this goes back to the whole philosophy that science never proves anything. We just have such a high probability that we have a lot of confidence in it. And that's a thing with scientists. So when we're doing hypothesis testing, which all inferential statistics, that's what we're doing, is testing this null hypothesis and the alternative hypothesis. So is there a really high probability that the null hypothesis is false or untrue? Do we have any evidence of that? And if yes, we can be confident that there's a relationship among the variables or that there's a difference between these two groups. Unless we can find some evidence, the null hypothesis stays. And that's what we do. We use inferential statistical analysis to test the null. So we run these tests. And the different kinds of tests depend on the research question that we've got and the design that we've got. And that's how we choose which statistical test to run. So the overall process that you use. First of all, you have to state the null and the alternative hypothesis. So we've got to figure out what the status quo is and then what the alternative to that would be. We always assume that the null is true. Then you set the level of significance. And the level of significance, I'll talk about this in a minute, but basically you say, I'm willing to accept this much probability of the mistake, of making a mistake in rejecting that null. So say you set your level of significance at 5%, p is less than 0.5%, you're saying that you're willing to accept a 5% chance that you're making a mistake if you reject the null. Then you collect the data and you calculate all the differences between the groups, and I'm really simplifying this, and then you calculate whether that difference is too large to be by chance. And that's where you come up with what's called a test statistic, and I'm going to show you that in a minute. And then you can either accept or reject the null based on your evidence. You never accept or reject the alternative hypothesis. All you do is come up with evidence about the null hypothesis. So, just to kind of wrap this up, you're comparing between two groups. There's two kinds. You're either comparing groups or you're showing relationships between the groups. The null hypothesis tells you there's no difference in the mean scores of those groups. They're the same. Your alternative hypothesis says, oh, there is going to be a difference in the mean scores between the groups. Now, if you're looking at the relationships, it's very similar. Your null hypothesis says that, oh, status quo, there's no relationship among these variables that you're studying. Nothing at all. Well, of course, you're trying to find evidence against that, and your alternative hypothesis would state that there is a relationship among the variables studied. Now, this is great grammar. How do we decide about the difference? This difference between groups, or the strength of the relationship. We look at what's called the level of significance. And what that is, and you do this before you do any analysis, you determine the level of significance. And it's the probability of a mistake by rejecting the null. You say, I'm willing to accept the chance of making a mistake in rejecting that null, in proving evidence or bringing evidence to reject the null. And it's called a p-value. And the P stands for probability. It's the probability that the results are by chance. So if I set a significance level of P equals 0.01, I'm saying I'm willing to accept a probability of 1 in 100 or 1% that the difference I found was simply by chance or a sampling error. I'm willing to accept that. And that's going to help me build how much confidence I have in my results. So if someone sets a P of like 20%, they're saying, I'm willing to accept a 20%, a 1 in 5 chance that my evidence just came up by chance. Obviously, we're not going to have much confidence in that. Whereas a 0.01, a 1% chance, that we could have a lot of confidence in those results. But the probability that you end up with is affected by several things. It's obviously affected by the size of the difference. If the difference between the groups is really, really tiny and very hard to detect, then you've got to be willing to accept a larger probability of making a mistake if you're going to see anything. It's also affected by the degree of error, how much error there is in the sampling that we're doing. And that's an unknown. You can't really measure that error in the sampling group. And last of all, and very important, it is affected by the sample size. If I have a ridiculously large sample size, I can have a very, very low probability threshold and show an effect. And yet it may not be there in anything that's worthwhile. If my sample size is large enough, I can show almost anything. So that if you're going to have the power and the confidence, you have to get your sample size just right. Now we call the significance level the alpha level, and you can see the alpha symbol there. You always set it, the researcher sets that before any analyses. And it should be spelled out in the article. You should be able to see what the alpha level was, the significance level. And basically what we're doing is we're setting a benchmark or a criterion for either accepting or rejecting the null hypothesis and how much we're willing to chance making a mistake. These are some very common ones that you will see in different kinds of research. 0.01 is very, very stringent. That researcher is saying they're not willing to reject that null. They'll keep the status quo unless there's less than a 1% chance they're wrong. 0.05 is very, very common, especially in educational research. And then you'll also see a 0.10 or a 10% chance, which is okay for small decisions or things that don't matter as much. You really have to set your significance level based on the seriousness of making a mistake. Can you imagine in medical testing, if I'm testing this this drug, which may have some side effects, but I think the side effects might be worth it if I've got this drug that will help people. But at the same time, I don't want the help that I see or that I can measure to be based by chance. So I don't want to make a mistake in saying that I'm going to reject the null and say there's a difference in these groups. So if in medical tests, they often go with that 0.01, a very stringent level, because people's lives depend on it. If I say that there's a difference there, reject the null, but it turns out that that was by chance, I could actually be killing people with this drug. Educational research is not usually life and death. We think it is sometimes when we're in the trenches, but it's really not. So a 0.05 is very common and very acceptable. And that's the researcher is saying, I'm willing to accept there's a 5% chance that 5% probability that all of this is by chance, and I shouldn't have rejected the null. Now, you'll read about type 1 errors and type 2 errors. So flag this chart if you need to, okay? What we're talking about is what kind of error we're taking a chance of making. And they kind of go against each other. A type 1 error, type 1, the first way, you reject the null, but it was really true. It should have stood. Nothing is going on, really. It's status quo, but your research says that there is something going on. That's a type 1 error. I rejected the null, and oh my gosh, I shouldn't have. Now, a type 2 error is just the opposite. It means that that the null is false. There's evidence out there somewhere, but I couldn't find it. So I let the null hypothesis stay. Type 2 error means something is going on between those groups or with that intervention or in those relationships, but I couldn't find it. So I do different things depending on which type of error I am most worried about making. And you will most often see people worried about a type 1 error. But I could argue that a type 2 error is awfully important. If there was some intervention that did some good, but I didn't find it, what a shame and what a waste to the world. So a type 2 error should never be discounted. Okay, to kind of bring this to a conclusion then, hypothesis testing. On the left-hand side, we accept that null hypothesis if you can't find a difference between the groups. It's too small for any kind of a confidence, and you have to say that any difference I found was probably just by chance, and a different group might have it, might not. Or you say that the relationship among those variables is so weak that it's probably just happening by chance. And in that case, the null hypothesis stands. Now, if I'm going to reject the null hypothesis, I have to find enough evidence to show that the difference between those groups is large enough, and I've got enough confidence in that it's not by chance that I found that difference. And if I'm talking about relationships, the relationship has to be strong enough to show up in my inferential analyses and not be likely by chance. So to wrap this up completely, get in your mind really clearly the difference between a null and an alternative hypothesis, because researchers will assume that you understand those concepts and will simply throw out that they rejected the null hypothesis in favor of the alternative hypothesis and different phrases like that. What they're doing with their inferential statistical analysis is they are doing statistical tests to gather evidence so that they can be confident in rejecting that null. That is very, very critical, and it's the hub, the essence of inferential statistics. You're testing the data to gather evidence with enough confidence to reject that null hypothesis. And there's always a significance level that's set, and that gives you the threshold of whether you're willing to accept the probability that the results are by chance. How much are you willing to accept that they're by chance?